How we doing, guys? Steve here with AmpFI, DIY Auto Tune, and today we are working on Project Foxbody 41. This car is piloted by a local team of guys who run with us occasionally when we're out with Jayzilla, and they've been having some problems with high RPM breakup, and it's ruined quite a few of their track days. Now, before they brought the car into us, they were not running our products. They were using a Brand X ECU. What we've done is we've created a jumper harness from the Brand X ECU to one of our prototypes. And what we're going to be doing is basically putting it through its paces, getting everything running on our prototype ECU, and in exchange for dyno time, they're going to be doing on-track testing for us. What we're trying to do is get a bunch of hours on these new prototypes before we release them to beta testers, to our dealers, and then once the dealers give us a thumbs up, then they'll be, well, released to you guys for use in your own projects. So unfortunately, of course, like all Mustangs, this one is really, really loud, kind of like the Coyote was. So because of that, we're not going to be able to get great audio while we're on the dyno here. So I'm going to do my best to explain what it is that we're doing, and then we'll make the changes and we'll, show how they affect the vehicle. I'm not going to be doing a complete retune on this on camera. As a matter of fact, you guys caught me in the middle of it. I already got up to 3,000 RPM steady state. But the goal here is I'm going to show you how I tackle some of the ramp pulls for power production on a vehicle like this that's quite rowdy. Maybe we'll touch on some of the idle issues that a car with a cam this rowdy typically has, how to get a smooth idle drop, and then we're going to talk about acceleration enrichment before the vehicle leaves our care. Now, that said, I'm going to do all of it on dyno, including the acceleration enrichment, and some of that is going to have to be tweaked trackside. No matter what, when you're on dyno, you're going to get really close, but you have to do those final tweaks trackside. It's a requirement. It's just to make sure that everything's really dialed in a real world environment with real track temperatures, without the hood open, without fans blowing on everything, providing you decent air. So let's go ahead and jump in and get started. And let's all make sure we're wearing our earmuffs on the dyno. All right, let's go ahead and get started. Alright, let's go ahead and work through a little bit of this steady state again. I'm going to start with the low RPM and work our way through this very quickly. Now, one of the important things to note is that even though you can see I have higher numbers here than here, when I started this, the coolant temperatures were much lower. Because the coolant temperatures were lower, some of the other modifiers, such as coolant temp modifier and air temp modifier, they're going to be affecting the tune differently. That means that really I'm trying to get heat into this while also working through this, because I do have a very limited amount of time to get this done. We're almost never going to be down at these 1500 RPM ranges on track. However, I want to make sure that they're fleshed out properly. That's going to give us really great drivability around the paddock. With that said, once I'm fully warmed up, I'll lower my steady state tuning back down to these values just to re-verify fuel. That's really important because we want to make sure that even though we're doing the tuning quickly, we want to make sure that, you know, before we get out there, these areas that are really difficult to hit or will otherwise give you a lot of trouble with the vehicle in motion to tune through, we want to make sure we get those while the vehicle's on the dyno. Alright guys, so one of the interesting things about this car is it does have a stepper idle valve conversion done to this Foxbody. Now, I'm letting the car cool off right now because I just got done with most of the steady state tuning before we get into ramps. So let's take a quick look at the conversion that was done on it, and then I'm going to show you what some of that looks like in the software and how I arrived at the settings that I'm using to get a nice clean drop back into idle. Let's take a look. All right, don't mind the bit of wiring mess going on. Obviously, they just did some of the conversion, and most of this is just kind of laying out of the way instead of being tucked, just in case we need to get to it to make any changes during this installation process. Once everything is working, it'll all get tucked away nice and clean, as you would expect any build. Now, one of the couple things that I asked them to do was to put an air intake sensor right here in the intake tube. Why? These Foxbodies are notorious for intake air temperature heat soak. And that's a phenomenon where the metal surrounding the sensor causes a very high temperature reading. Normally, it is right here in runner number 5 on the small block Ford, and that sensor is very hot to the touch currently. Now, Ford had a great reason for doing this. Ideally, you want to get the temperature reading right where it goes into the valve. And while in theory that works out great, with these large cast aluminum manifolds and the relatively slow change in temperature reading on a thermistor, we get this heat soak effect. And you can see that where in a typical Foxbody, your intake air temperature sensor is going to start matching the coolant temperature. At any extended idle or after a run, the temperature will come back up. It's pretty obvious when you start a pull on the dyno or you start a run at the track, you can actually see the intake air temperature go from about coolant temperature, and it will begin to drop rather drastically as the vehicle picks up speed. But it will never make it down to ambient temp. Now, they've got a nice hot air intake on this car currently, but with the intake air temp sensor, or the mat air temp sensor, or IAT, installed in the intake tube here, once they get this filter out of the engine compartment, what we should see is about a 30 to 40 degree Fahrenheit over ambient temperature reading that will quickly drop to ambient temp, or right around ambient temperature, once they're actually under speed on track. And that's going to get us much better manifold air temperature fuel trims in the long term. Now, stepper valve. The stepper, this Foxbody has been converted from a PWM valve to a stepper valve. And while they tune very much the same, some people seem to believe that a stepper valve is a little bit more accurate than a PWM valve. I don't really see much of a difference tuning-wise between the two. This stepper valve, really it needs a little bit more of a gasket around the pintle. What's happening is there's a very narrow range that this stepper valve actually works in for controllable idle speed, even though I've reduced the angle of the throttle quite a bit from when it came in. The lowest idle speed I could achieve with the idle valve fully closed and only about 5 degrees of ignition timing in this motor was around 850 RPM. I reduced the throttle by about 10% opening, and now I can easily achieve a 750 RPM idle speed. However, the engine's not really happy around there, so I target to maintain about an 850 RPM idle speed. Now let me show you in the software what I did to get the values that we're using to get this not only idle speed and control, but to make sure that it drops back into idle appropriately. All right guys, so let's take a look at the settings I used for idle here. So like usual, I kind of set everything up in closed loop idle. So our idle control is set to closed loop. I'm using some rather small time step sizes and whatnot. I really prefer to home a stepper valve open rather than closed. The reason why I like to do that is if you just jump in and turn everything on and hit the start button, what you may run into is if you're homing closed rather than open, you may catch the valve in the full closed position during a crank. If that happens, then the valve's going to be closed and you're going to get a really low or slow idle speed, or maybe a start and stall condition. And to stop that, I home in the open direction. Now, on all of our new ECUs that will be coming out, especially this prototype competition series ECU, we have gone to much better stepper chip, and I can just leave power on for always on for power between steps. Okay, closed loop idle here. Now, what I found after I lowered the amount of throttle angle by backing out that idle screw is that we get our lowest idle position at around 60 steps. Now, above 140 steps, we have a very, very high idle. Although I don't really set a maximum, I just left the idle valve maximum steps at 250. I'm adding 5 steps for a dash pot adder. When we're dealing with our closed loop tuning, something to remember about closed loop PIDs is that this is a C-type loop. The C-type loop means you're going to tune your I first, then your P term, and then finally, if necessary, add a small D term. So I is basically what you're going to focus on for idle loop tuning 100% of the time. Then you add P term in small amounts until you get an appropriate response to an immediate idle change. And then you only add derivative term if you absolutely have to. I use a value of 1 out of habit. Anything above, say, 5 to 10 on your derivative gain is going to slow the loop down substantially. So this is the reason why I'm using 75p, 165i, and a derivative of 1. Here's my initial values, and here's my closed loop target idle curve. So you can see I'm targeting an 800 RPM idle speed once the engine is fully warm, and I've got 111 steps set for that idle speed. Now, that does not mean that when we're at idle, we're going to be sitting at 111 steps. That means that when I blip the throttle, or I clutch in, or I come off, as the idle drops back down, I want to start at 111 steps, and then closed loop is going to lower that value to get me down to my stable idle speed. So when we start the car and we let it idle down and I blip the throttle, you're going to see the idle stepper go between 111 and 116 because we are adding 5 in the dash pot adder. And then you'll see closed loop idle kick on, and then the stepper valve will close to drop the idle the rest of the way. And how I set this is when the engine is hot, I sit here and I change this to different values, 800, 900, 1000, and then I figure out what initial value do I need to get a nice clean drop into idle. I always want to come in slightly above the idle speed I want and then drop in cleanly. Now, an engine like this that's got a very choppy cam, we cannot just look at the idle valve. My idle advance settings here, that's this timing correction curve and my idle advance timing. What this means is that as soon as we go into an idle state, instead of using the ignition table, I am going to use this idle advance timing curve right here. So when my fuel load is low, when I'm under heavy vacuum, I'm going to use this advance value, and then this advance curve is going to be modified by this timing advance curve. And these two work together to maintain a strong, solid idle speed. So you're not going to be able to hear me talking while this is running because the engine is so loud. We're going to try and see what we can get out of the audio. But what I'm going to do now is I'm going to start the engine, and I'm going to show you how this drops back into idle, so you can see how I go through the process and what we get out of it. What we're going to focus on is I'd like you to focus on the RPM, the stepper position, our target, ignition timing right here, and our air-fuel ratio. Those are the most important things to focus on when you're tuning idle, okay? Your ignition timing is very important for how the engine's going to idle. Your air-fuel ratio needs to be stable. And if you're excessively rich or excessively lean, that's definitely going to affect the quality of the idle that you get out of the vehicle. So on that restart, it was pretty lean. Now, I wasn't recording the screen, so you don't know how lean, but I'll tell you, it was lean. I had about an 18 air-fuel ratio that was displaying. So what I'm going to do is extend my ASE taper, because the car has been sitting for about 20 minutes since it was last started. And now that I've extended that ASE taper, I'll show you how much I added to it, and then I'll show you the difference. Okay, so we had that really lean restart. So after start enrichment is one of those things that's very important when you're dealing with a hot engine. And I had a scenario here where on a restart, I had a very lean air-fuel ratio. So looking at our taper value here. And I had this taper at 1250. And that wasn't keeping the fuel in long enough to rebuild the fuel in the intake manifold to get us back down to our normal, stable air-fuel ratio. So what I'm going to do is I multiplied by 1.8 when it's super hot here and really extended that taper out quite a bit. And what we're going to do is restart and see how lean are we this time. Now this is our competition ECU has a built-in wideband, so we're just going to let it go through its warm-up process. And you can see the ASE taper is sticking around for a much longer period of time. We're adding quite a bit. We're adding fuel for much longer than we were previously. And the idea is we need to keep that fuel around to rebuild that layer. And as that fuel finally disappears, we can see that we are back to our normal, stable air-fuel ratio there at idle. All right, now that that's complete, let's go back to talking about closed loop. Now, we can see that I'm sitting right around 70 idle steps currently. Now, What I want you to do is when I flip the throttle, watch how many steps that goes to. Right here, you can see our dots pointing right at this column. We're going to pull 111 steps plus the 5 steps from right here for our dash pot adder for 116 total. The idle should come in a little high, right around 1,000 RPM, and then settle in to 800 in a reasonable amount of time. Okay, nice response. So the idea here is we want the idle to come in above our target and then settle in nicely so we don't end up with a stall condition. I'm pretty happy with that. Now, what I did to derive these values is I set my target closed loop, and then I simply went through and figured out what value do I need. So let's set a value of 900. Now notice we went to a higher number of steps because we're now pulling from the 900 column. So 115 plus the 5 should give us 120. You can see we come in above our 900 target and then settle it nicely. This is just a bit of trial and error on my part. What I did is I set my value and then I adjusted my initial value column until I got the idle to drop in how I expected. You can see it drops in nicely. Exactly what I was hoping for. Now, for that really low idle, because this has got a super chop cam in it, sounds really good. I do not like to drop directly into idle at this low idle speed with a choppy cam like this. That's just asking for stall condition issues. That's why I had more steps or PWM percentage than necessary to get the idle to drop in as expected when I need it to. I'd rather have a slightly high idle when it drops in and then let it come down over time than have a stall condition. Now, these initial values are only half of the equation. Ignition timing plays a crucial role in how well the vehicle is going to drop into idle. We can see that right now we're pulling about 15 degrees of ignition timing from our curve because we're in the idle state. And we can see our ignition timing in real time is moving around. Why? Well, it's being adjusted by our timing correction curve. And the timing correction curve is using ignition timing to control our idle speed or help control our idle speed. Ignition timing is much better at controlling idle speed right now. I like to think of ignition timing as instant changes to idle speed, and the idle valve is a slower change for idle speed. Now, this works very well with choppy cams or large cams. A lot of your N-line or smaller displacement motors may actually become upset with this amount of timing correction. Let me show you what happens to the idle if I remove this timing correction. I'm just going to take these and set them to 0. See, it takes a minute, but the idle speed is not quite as clean as we'd like it to be. It doesn't stay as close to target. See how it's dropping down to the 600s before climbing back up? Now I'm going to put that back. can see that we're maintaining our idle target much tighter. As a matter of fact, these are actually rather easy values. I can tighten up right here, right around my 0 point. And what this means is that when we get negative 25 below target, we're going to add 2. When we get 25 above, we're going to subtract 2 degrees of timing. And now we can see that we're maintaining our idle target much, much tighter. You can get even more aggressive than this if necessary. It really depends on the application. But I don't like to get too aggressive because it does take away the chop of the can. Okay. Now, let's watch what happens when I change things a few times. I am going to make all of this 15, and we're going to see if the vehicle stalls. So much slower the idle drop, and you hear the backfires. That's because ignition timing was much lower as we came through that decel region. We do drop back into target much faster, but the concern here is on track or under normal conditions, we may have a stall. Watch what happens when we add a little bit of timing in that decel region. See how the idle slows down a little bit in its descent? So it slows the idle drop, and it makes it a bit cleaner as it drops in. You can get too aggressive though. See how slow that was? We don't want to get too aggressive with that. That's a nice drop in idle. All right, guys, we just got done talking about idle tuning and kind of how I went about it on Foxbody, on Project Foxbody 41 here. And I think what I'd like to do now, since a lot of you have asked for it, is cover a little bit of acceleration enrichment tuning. Now, because I don't have a whole lot of time to get fancy on this particular tune, I'm just using basic time-based acceleration enrichment, which, to be honest, is all I ever use on my own vehicles as well, because once it's dialed in, it works really, really well. At some point in the future, I'll get into those more advanced acceleration enrichment strategies. But let's take a quick minute and let's review what I've got set up to get a really crisp throttle response out of Foxbody 41. All right, so let's take a look at acceleration enrichment. So my basic Accel Enrich settings here are just time-based AE, and that's all I'm using is basic time-based acceleration. Now, because this vehicle has low map at idle, and because the idle is erratic, I don't want to take the chance of having acceleration enrichment improperly trigger at idle. Therefore, I've chosen to use solely throttle position based acceleration enrichments for this particular build. So I like to use a curve on most vehicles. I found something that looks about like this to work very, very well. Let me expand this so you can get a really good view of what we're working with and what I'm looking at here. So I like to start my acceleration enrichment at a relatively low TPS dot. Now, TPS dot is rate of change of the throttle position sensor. And even though I'm triggering at this relatively low 50% or 50% dot, that doesn't necessarily mean I'm adding a lot of fuel. This is in this system is set up as a percentage. This is not a pulse width adder. This is a percentage of the current fuel being injected added on top. Now, it's not quite that simple. We also have an amount of time that we're going to have it sit around. For simplicity, I set this one to time. Usually I use a number of ignition events. So I can say I want 20 ignition events rather than say 0.2 seconds. Ignition events works better for me because that means that the fuel is basically, it's going to bleed off faster in the higher RPMs because you have more ignition events. However, it also means that we can get a little bit more aggressive with those values. At higher RPMs, acceleration enrichment it's less important than especially that right off idle throttle response. So something important to note here is that if you're going to change your TPS dot here, I also change my threshold to that same value, so both of them are set to a value of 50. I do not cut fuel or use a enrichment. I leave my decel fuel value at 100%. I prefer not to remove fuel when I lift. I do that in the fuel table. I don't even use overrun fuel cut. 20 and 130 work well with pretty much every build, so I just leave them at that. On these domestic V8s, I have found that between 2,500 and 6,000, that's my tapers. So below 2,500 RPM, I want that full acceleration enrichment when I hit the throttle. And then we taper from that full enrichment at 2,500 to no enrichment at 6,000. So when we're doing these steps, I like to set them at 50, 120, 250, and 500. You can sit and play with the throttle and see, how aggressive different throttle changes affect your throttle position, and try and play the how fast can I get the pedal to move game. What I've found though is that generally speaking, those big breaths of air are always going to need somewhere around 30% fuel. So whatever my highest TPS dot value is, generally I set that around 30%. And my smallest TPS dot value is generally within 5 to 10%. That changes application to application. And then the shape of the curve looks like this almost every time. As a matter of fact, I bet if we pulled up the tune for the E30, my acceleration enrichment curve will probably look fairly close to this because this is what I've found works best, at least in the tunes that I've done over many cars. So it's going to get loud here for a minute, and let's dial in some acceleration enrichment. Now I'm going to do this at idle since it's very difficult to do this loaded on the dyno. However, what I'll do is I'll set the dyno up at steady state at around 2,000 RPM, and then we'll do some tip-in tuning during steady state. All right, now what I'm looking for here is I'm looking for when I tip in, I want to see the air-fuel ratio go slightly rich. These domestic V8s like this small block Ford, when I tip in, I want to see between a half point and a full point air-fuel ratio in the ridge direction. We can see that. We go rich. Notice that when I hit the throttle, we don't get a lean spike. If we get a lean spike, we may need to add a little bit more fuel. We are going rich. Now that's probably a bit excessive on that big end. Got a little bit of a lean spike there. Notice with that fuel decrease, now when I tip in, the air-fuel ratio is going slightly lean instead of rich. Let's see if we can see it instantly in the air-fuel ratio here. So what I'm going to do is I'm going to increase this back to where we started. Now, I could probably get some efficiency out of this by reducing the amount of tip-in fuel I have. However, from previous tuning, I can tell you that if I do remove any more fuel than I have in it right now, I'm going to start getting lean pops, even though the wideband doesn't show it. I like to tune my acceleration enrichments by feel rather than through a sensor. That throttle response. It wants more fuel on tip-in, regardless of what the sensor says. All right, I'm going to go ahead and load the dyno at 2,000 RPM, and then we'll do a little tip-in and see what it does. We can see that the air-fuel ratio went fairly rich, down into the 11s. However, that seems to be what this engine likes on those large throttle changes when it takes that big breath of air. I am going to leave it like this, and we're going to get some on-track data and then adjust from there once the driver gives me their feedback. They may say that the throttle feels a bit soggy. If it feels soggy, that lets me know that I'm going to need to back a little bit of this acceleration enrichment fuel off. Now, you're not going to be able to hear me talking. I'm going to increase this to 3,000 RPM, and we're going to do this test again. is that the acceleration enrichments that we currently have set are working. The throttle response feels good. It sounds good in the exhaust tone. I'm going to leave it exactly where it's at. I hope this has been helpful. All right, guys, now that all the steady state tuning is done, we've covered idle, we've covered some acceleration enrichments. What we're going to do is, the car's nice and warmed up. We're going to do some ramp pulls now. Now, because the steady state tuning was done, and I've already done a few ramps, the fuel table is pretty darn dialed in. But what I'm going to do is show you what I've been working on and kind of a bit through my process. We're going to move air-fuel ratio around a little bit. We're going to move ignition timing around a little bit. We're going to see, can we make a little bit more power today? What I'm going to do is I'm going to go ahead and clear all of the auto plots that we currently have up. This way we start from fresh. We'll do a pull. We will then work on fuel first. We'll lean fuel out. We'll add fuel. We'll go 0.3 AFR from our baseline here, lean, then 0.3 AFR rich, see which direction makes more power. That'll help us decide where do we want to put the air-fuel ratio target. Then we will start working on moving our ignition timing. First, we'll decrease ignition timing and do a pull, and then we will increase ignition timing and do a pull and see what nets us the most power. Okay, that was our baseline pull. What we're going to do now is we are going to change our AFR target, and first we're going to go rich. So I'm going to decrease our AFR target by 0.3 under wide open. Let's do another pull. So what we can clearly see if we take a look at the dyno right there is that when we decreased our AFR target by 0.3, we had a power loss across the board. This tells me that we're going in the wrong direction. This is too much fuel. The engine's a bit too fat. Let's take a look at what our targets are currently. Right now I'm starting the pull around 12.5 target, and by the end of the pull we're targeting around 12.1, 12.2 air-fuel ratio. We're getting exactly what I would expect. This is an air-fuel ratio target that I would run at a mild boost application all the way up to kind of moderate boost depending on the build. It's not a surprise that we lost power. What I'm going to do is I'm going to put the 0.3 back. This is our baseline. And now I'm going to increase our AFR target by 0.3 from baseline. And now we're going to target from 13.1 to about 12.8 air-fuel ratio. And let's see if we make any more power than baseline. All right, I'm going to shut this down so you guys can hear me talk. Okay, now what exactly are we looking at here? we can see that from baseline, increasing our air-fuel ratio target on this build has increased horsepower. We did this real time with no downtime, no cool-off time between pulls. Our baseline pull is red. Our green pull was more fuel. Our orange pull was less fuel. So our baseline made the most power. But is that because the engine was shut down and it was the coolest pull? What we're going to do is decrease our air-fuel ratio target back to the baseline and see, do we make baseline power numbers again? Or is this just heat soaked from back-to-back pulls on the dyno? Remember, if we're going to make changes, we have to make sure that we make changes with good data. Otherwise, we're just guessing. There they are. All right, let's get this pull started. Okay, what we can see here is that there's really not a huge swing based on our air-fuel ratio target in that 0.6 air-fuel ratio range. What this tells me is that the richer target may make more power with more ignition timing, and it may not. What we're going to do is we're going to leave the air-fuel ratio target at our baseline because that's what I usually target when I tune this engine, or this engine family. It's between 12.8 to 12.5. Kind of like a Coyote or an LS. These larger displacement, domestic, pushrod D8s really do like to be a bit richer than most other engines where we usually target 13 to 13.3. These really like to be in about that mid-12 range, especially in the higher RPM. All right, now let's play with some ignition timing. So here's the ignition timing we're currently looking at. The first thing I'm going to do is I'm going to remove 2 degrees of ignition timing, and we're going to see what that does to power output. Now, because all of these pulls back to back made about the same amount of power, I'm going to go ahead and get rid of the last few. All right, now keep in mind the green line, that's the one that we're focused on here. All right, so I'm gonna remove 2 degrees of timing. Had a net power loss. We can see the entire torque curve is less than the green line. That means we definitely have a net power loss here. So what I'm going to do now is we removed 2 from our baseline. I'm going to go ahead and go back to baseline plus 1 degree. All right, let's see if we make any more power with an extra degree of timing over baseline.
Definitely made more power than the orange pull, but we did not beat the green line.
What I'm gonna do is, just to verify, I'm gonna take that degree of timing over baseline back out, and we're gonna do one more pull, and we're going to see, can we match the green line?
That looks like a power loss from the extra degree. However, we've been doing back-to-back pulls. The engine is properly heat soaked. So I think in order to figure out exactly what's going to make the most power here, we're going to have to let this engine cool off between pulls. But this engine's going to be absolutely thrashed on track. Because it's going to be absolutely thrashed, there's really absolutely no reason for us to put more timing in it than necessary. Yes, all of us want as much power as possible. However, in this scenario, the best thing that we can do is try and flatten that torque curve out. So let's work on doing that. So, we have a small horsepower dip right around 4,000 RPM. Let's add timing just there. Let's work on 4,000 RPM and see if we can flatten that out. Now we're going to need to be careful around 4,500. You see 4,500 is peak torque. Generally, if we're going to run into detonation issues, it's going to happen at peak torque. Now we can see that the gray pull, we managed to match the green pull. And these back-to-back pulls really put a lot of heat in the motor, but sitting here idling, we were able to get the coolant temperature to come down some. Now, we can definitely see we made some gains around 4,000 RPM. So what I'm going to do is I am going to clear the last few clocks. We're going to leave just the red clock. I'm going to let this car cool down a little bit, and then we're going to see what it does after a 5-minute rest.
5 minutes later.
All right, the hero pull starts in 3, 2, 1. are pretty solid numbers for a naturally aspirated 347. This is Trick Flow, 170cc head top end kit. This is a pretty healthy build. Great numbers, especially on a hub dyno. All right, guys, thanks for joining us while we tune out Project Foxbody 41. If you want to see us cover anything else with this vehicle or others, let us know. Reach out.